This lesson deals with resistor-transistor logic gates. You can find these notes in the ECE302 ebook in Chapter 3, starting on page 39. What's shown here is what's called an Rtl inverter. Consists of one BJT, a 640 ohm collector resistor, and a 450 ohm base resistor. This was the first commercial logic family that was introduced by Fairchild Semiconductor back in the 1960s. We're going to show that this is actually an inverter. Let's assume that VBE on is 0.7, VCE sat is 0.2, and beta F is 100. Under what conditions of input will we be in cutoff? Let's put in the model for the BJT to be in cutoff, and that would be an open circuit between the base and the emitter, and an open circuit between the collector and the emitter. We have no current flowing, and for to be in cutoff, this needs to be less than or equal to 0.7. When the input's greater than or equal to 0, but less than or equal to 0.7, that would be the condition for the voltage here. If there's no current flowing here, there's no drop across the resistor. This node voltage here is the same as this one. In other words, this voltage is equal to minus 0 plus 3.6. Sometimes this resistor is called a pull-up resistor because it takes the output and pulls it up to the power supply. What would be the conditions to put the logic gate into saturation? Let's put the model in for saturation. Between the base and emitter, we have VBE on, 0.7. Between the collector and the emitter, V sub CE sat, which is 0.2. Now let's solve for the collector current and the base current and check their ratio and whether they're greater than or equal to 0. The current in the collector is the current in this resistor, so it's this node voltage, VCC minus Vout divided by 640. 3.6 minus 0.2 divided by 640 is 5.31 milliamps. To be in the active region, the ratio of I sub C to I sub B needs to be less than or equal to beta F. That means that I sub B needs to be greater than or equal to I sub C over beta F. I sub C was 5.31 milliamps, beta F is 100, and that gives me 53.1 microamps. The base current is the current in this resistor. Let's go around this loop. The rise in voltage is V in. The drop is IB times R sub B plus 0.7 back to ground. That's this equation right here. But we know that I sub B needs to be greater than or equal to 53.1 microamps. That means that Vn needs to be greater than or equal to 53.1 microamps times R sub B of 450, and that's 0.724. In ECE 201 and 202, we derive transfer functions, but in electronics, because things are nonlinear, all we can do is do a sketch of output versus input. Let's do that with what we've already calculated. When the input is less than or equal to 0.7, the output is 3.6. In other words, the output's high. We just showed that when the input is greater than or equal to 0.724, the output is equal to 0.2 volts. This would be a low case. So here we've got a logical 1, here we've got a logical 0. We know that when Vn was less than or equal to 0.7, we were in cutoff, and when Vn was greater than or equal to 0.724, we were in saturation. What about between those two values? Well, since we've covered all the conditions to be in cutoff and in saturation, it's most likely in the active region. So let's put that model in and see whether it's consistent. Between the base and the emitter, we'll put the VBE on of 0.7. Between the collector and the emitter, a current-controlled current source of beta F IB. And now let's solve for Vout. Vout is going to be equal to, if we go around the loop this way, minus I sub C times R sub C plus V sub CC. That's this equation right here. Now what is I sub C? Well, it's beta F IB, and I sub B is the current in this resistor, which is this node voltage Vn minus 0.7 divided by R sub B. It's this equation right over here. Substitute that back in. So Vout is equal to VCC minus beta F times IB times R sub C. In this case, VCC is 3.6 volts, beta F is 100, R sub B is 450, and R sub C is 640. If we take all the things that don't multiply Vn, that would be 3.6, a minus 100 times minus 0.7 divided by 450 times 640, you get 103.2. And the things that multiply Vn are minus 100 divided by 450 times 640, and that's 142.2. If you plug in this equation, Vn equal to 0.7, you get 3.6. If you plug into this equation 0.724, you get 0.2. In other words, this equation connects up these 2 points. Go from cutoff to saturation, we're going to pass through the active region. There are many different technologies for implementing a logic gate. We need some way to compare them. One way to do that is with a logic level diagram. Let me explain the following. For an inverter, we had an input that whenever we were below that value, the output would change state. We're going to call that V input low. Then we also had calculated a V input high, that whenever we were greater than or equal to a number, the output changed state. And we had calculated 0.7 for V in low and 0.724 for V in high, but the manufacturer suggests using 0.9 for the input high. This is because the value of beta F, VBE on, and VCE sat varies as you manufacture transistors. On the output side, we had an output that was high and an output that was low. In our case, the output high was 3.6 and the output low is 0.2. You can define these for any logic inverter and can use as a way of comparison from one technology to another. Given these numbers, you can also do some calculations. First one's called logic swing, and that's the difference between these two numbers. In this particular case, it'd be 3.6 and 0.2, or 3.4 volts. The bigger this number is, the longer it takes for a transistor to switch from one level to another, and so it affects speed. The transition width is the difference between the input high and the input low. In our case, it's 0.2 volts. And what it's saying is that if you wind up in this transition region, you don't really know what state you are. But if you stay below 0.7 or above 0.9, then you can guarantee that you're cut off or you're saturated. Electronics is exposed to all kinds of noise, from cell phones, from motors, things that radiate energy. The logic gate needs to be able to withstand noise. And we're going to find this next term called noise margin high as a measure of this. That's going to be the difference between these two numbers. And what this means is that if this is the output of a logic gate, but that now becomes the input to another logic gate, how much noise can I tolerate before the logic gate changes its function? Let me do some numbers here. Suppose I'm sitting at 3.6 volts at the output of a logic gate, and now hook this up to another logic gate. How much noise could I have before I change the function of it? In other words, if applying an input that's high, that's going to force the output to go low of the next logic gate if it's an inverter. It can go down as far as 0.9 volts, and that means I could tolerate a noise spike that would drop the voltage from 3.6 to 0.9 and still maintain the functionality of the inverter. The noise margin high is 2.7 volts. I can withstand 2.7 volts of noise before things change. I could withstand a pulse going in this direction. It wouldn't change things. It might damage the IC, but it wouldn't change the functionality of the chip. There's also a problem on the low end. Suppose this is my output of a logic gate and it's feeding another one. How much room do I have for noise here? Let's put some numbers on it. I'm sitting at 0.2 volts, and now I get a pulse of noise, but that pulse can't take me any higher than 0.7 volts. And if I do, then I get into the transition region and don't know what the output's going to do. Noise margin low is only 0.5 volts. These two numbers, the smaller of the two is what you have to worry about. A problem that's common to bipolar logic gates is a thing called fan-out. This is the number of load gates that you can connect up and still maintain functionality. Suppose we have an inverter, and we now hook it up to N inverters. How big could N be before things stop working? If you apply a signal here that's, say, greater than 0.9, you're going to saturate this transistor, and this voltage is going to drop to 0.2 volts, and all of these gates are going to be cut off. So there's no limit on the number you can hook up. But suppose now you cut off this transistor by applying something less than 0.7. This cut off, then this is going to supply current to the N gates. This voltage here, nothing hooked up, is 3.6 volts. But now as you begin to draw current, this voltage begins to drop, and the smallest that this can be is 0.9 before we lose functionality. Let's figure out how many gates we could hook up if this could drop to 0.9 volts. This current is equal to this current all the way through here through N. And the current that's entering here is 3.6, or VCC, minus 0.9 divided by 640 ohms. And that has to equal this current plus N more. N times the difference of these two node voltages, which is 0.9 minus 0.7, and then the current would be dividing that by 450 ohms. And this is shown on the bottom of the page. We can now solve for N. Cross multiply by this, I get 450 divided by 640, VCC minus 0.9, then divided by 0.9 and 0.7. When VCC is 3.6 volts, this is 9.49. You could increase the value of this voltage and increase the number of gates that you can hook up, but then power consumption goes up. There's always a trade-off as we do one thing versus another. But we get 9.49 gates. Now you can't have a 0.49 gate. You would have to round down this number, so the number of gates that you could hook up would be 9 or less. With this last example, if I were to hook up 9 gates, my noise margin high would be dropping from 2.7 volts to something near to 0 because I'm drawing current through that collector resistor of the first gate. In reality, you may not want to hook up 9 gates but something less depending on how much noise you need to tolerate. Another thing to note here is that the term fan-out is commonly used incorrectly and refers to the number of actual gates hooked up. In other words, if you hooked up 4 gates, they would say the fan-out is 4. No, the fan-out is 9 for this logic family. So when you read application notes or magazine articles, you have to do that with a critical eye and look back to definitions that we had in our course or other things that you can find in textbooks. Consider taking our basic inverter structure and repeating this part of it multiple times. So give me a 3-input gate. We'll show that it's actually a NOR gate shortly. Whenever any one of these inputs is high, the output goes low. If the output goes low, then this is equal to 0.2 volts, and we draw a current back through here if this one went low, or this one, or all of them. So whenever one or more of these are high at the input, the output goes low. The only case that's different is when all 3 of these hooked up to 0 volts, and that cuts off all 3 transistors. When that occurs, no current flows because we've got 3 open circuits, and then the output voltage again is pulled up to the power supply. This is shown on the next page. Let's summarize what we just talked about. Whenever one or more of the inputs is high, the output's going to go low. We have basically 0.2 volts in parallel with itself if it's done multiple times. The only case that's different is when all 3 inputs are 0 and we cut off all 3 transistors and the output is pulled up to the power supply. And we can map this into a logic table where 0 volts corresponds to logical 0 and 3.6 volts corresponds to logical 1. Now, if you had a course like ECE302 or a course in logic, you could then write a Boolean expression for what's here. We talked about an OR function in Chapter 2. Whenever one or more of the inputs was high, the output went high. And here just the opposite is happening. Whenever one or more of the inputs is high, the output's low. That's the OR function complemented. And these are resistor-transistor logic gates.